Okay, so if you've been working through the videos, I've asked you to make Lewis structures a few times, even though you may not have known they were Lewis structures. You may have been able to predict them, but you also may feel like you were lacking framework. So in this video, we're going to take a minute and go over the protocol for predicting and writing out the structures of different molecules. So why do we want to learn these Lewis structures? Well, because learning Lewis structures and how to draw them will help us predict and understand the structure of fibers and dyes. If we understand and know how to talk about structure, then we can talk about function. First, to start, we will encounter two different types of structures in this course. Linear structures, which have between 2 to 3 atoms, and then wheel and spoke structures, which have 3+ atoms in them. So there's two possible types of arrangements that we're going to make. If we do anything wonky, I'll give you a skeleton starting out. And generally speaking, we put the less electronegative atom in the center, unless it's hydrogen, which always goes out on the outside. I've got the protocol for determining Lewis structures in the skeleton notes, but I'll demonstrate it by walking through some practice examples. So let's start with CO2. So first we start by counting the number of valence electrons in each atom. Carbon has 4 valence electrons, and each oxygen has 6. 4 plus 6 plus 6 gives us 16 electrons to work with. Don't worry, we don't have any charges because CO2 is neutral, so we keep the same number of electrons. Next, we write out the skeletal structure. So with the exception of hydrogen, and we have no hydrogens, we put the least electronegative atom, carbon, in the center. We put each oxygen on the outside. Then we draw a single bond between each atom. We count up how many electrons we've used. 2 and 2 makes 4 electrons, and then we subtract it from our starting value. And we have 12 electrons left over. Next, what we do is we fill the octets of the outermost atoms with lone pairs until we run out of electrons. We have 12 electrons, so we'll put 3 pairs on each oxygen. Now we're going to go ahead and count up our electrons. 6 plus 6 plus 2 plus 2 gives us a total of 16 electrons. So we've used up all our electrons. But are we done yet? So one of the most important things is that all of our atoms have a complete octet. Specifically in this course, carbon will always have an octet or make 4 bonds. In this particular setup, carbon only has 4 electrons or 2 bonds. It's missing 4 even though each oxygen has 8. So what do? We find ourselves in a situation where an atom doesn't have enough electrons. We make a second or a third bond to give us double and triple bonds. So in this case, let's take one lone pair we've assigned to an oxygen and make it share between the oxygen and the carbon. This is good because that oxygen is now making 2 bonds, which we know from the first video is oxygen's preference. But carbon still needs 2 more electrons or 1 more bond. We don't want to do it with this oxygen because this oxygen is already making 2 bonds, and so we can turn to the other oxygen, which is only making 1 bond with carbon. We'll take a set of lone pair electrons from this oxygen and use it to make another double bond with carbon. So let's take a step back and look at our answer. How do we know it's right? Well, first of all, let's count our electrons. We have 4 bonds, so 8 electrons there, and then 8 electrons coming from the 4 lone pairs on the oxygens. 8 plus 8 gives us 16, which is the number of electrons we start with. Then we make sure we have a full octet or 8 electrons on each atom, or a duet if we're a hydrogen. Check, check, and check. Finally, another signal can be if the atoms are making a correct amount of bonds, although we won't always see this happen. So atoms like to break rules. But for now, carbon is making 4 and each oxygen is making 2. So we're good to go. Now I'm going to let you pause and practice on your own with NH3. Give it a try and I'll walk you through the solution. So we start with valence electrons. We have 5 coming from nitrogen and 3 coming from hydrogen, for a total of 8. We've got 4 atoms here, so we're going to arrange them. Well, technically, hydrogen is the least electronegative atom. But hydrogen can only make 1 bond, so it always goes on the outside no matter what. So we put nitrogen in the center, and then we put the 3 hydrogens around the nitrogen. We start by drawing a single bond between each hydrogen and the nitrogen to create our skeleton. We tally our electrons and we get 2, 4, 6 electrons. So we have 2 electrons left, but all of our hydrogens have a duet. So what do we do when we have leftover electrons, but our outer atoms have the right amount of electrons already? We put a lone pair on the central atom. So we'll go ahead and we'll put a lone pair on nitrogen. Okay, so let's step back. We've got 2, 4, 6, 8 electrons. Check. Each hydrogen has 2 electrons, and our nitrogen has 2, 4, 6, 8 electrons. Check. Finally, each element looks like it should. Hydrogen makes 1 bond, and then nitrogen makes 3 bonds and has 1 lone pair. So we're going to do 1 more on the next page. Alrighty, so let's pause and practice here. That's the situation when we see a charge rather than a neutral molecule. So go ahead and in this case, we have NH4 plus ammonium, which you may recognize in the polyatomic ion chart. Okay, so we have 5 electrons coming from nitrogen and then 1 from each type of hydrogen for a total of 4. 5 plus 4 is 9. But we don't actually have 9 electrons. Why? Well, because we have a plus. For every plus sign, we lose 1 electron. And for every minus sign, we gain an electron. So we actually have 9 minus 1 equals 8 electrons here. Then we arrange our atoms and set up our skeleton. H is always on the outside, so we're going to put N in the middle, surrounded by 4 hydrogens. We draw a single bond between the nitrogen and each H atom. Now, to figure out what to do next, we count the electrons, and we have 2, 4, 6, 8. Okay, so we have 8 electrons. 8 electrons is what we started with, so we have no electrons left to work with. So no more bonds drawn. But do we stop here? Well, not quite. When we have a molecule with a non-zero charge, we slightly adjust our structure to indicate this is the case. We put a set of brackets around the molecule and then put the charge on the top right-hand side of the brackets to indicate the structure inside has a charge. So how do we know if this is correct? Well, every atom has the desired amount of electrons, even though nitrogen is making more bonds than we might predict. Each hydrogen has 2, and the nitrogen has 8. Nitrogen, again, is not acting like we predicted, but sometimes atoms act differently than we predict, especially if they're part of a charged molecule. What matters here is at the end of the day, the charge works out, and all of the atoms have 8 or 2 electrons.